now that we have an understanding of how this particular system works, and we have seen how we model this particular system mathematically, it's now time to see how the system is modeled in MATLAB. So we are going to use BPSK modulation, and we're going to define our modulation first, and then we are also going to define our EBNO, as well as the number of packets or a number of iterations in each EBNO. And we are also going to define the power levels of our receivers, that is user 1 and user 2, as well as Bob. And we are going to assume that they all have the same power, and we can define them this way. And we are going to define our FFT size as 64 and our guard interval as 16, essentially to prevent intersymbol interference, and our symbol duration as well. So this program basically involves two major for loops, where the first for loop goes over each EBNO, and the second for loop goes over the symbols we're transmitting, because here we define that basically goes over each packet that you are transmitting, because here we define our number of packets. So we come here now and we define our BER. We initialize them. We do some initialization in here by initializing our BER of user 1, BER of user 2, BER of user Eve listening to user 1, BER of Eve listening to user 2. And we also define some other BERs here, internal BER, and basically user 1 listening to user 2, user 2 listening to user 1. This is what we call internal eavesdroppers. And we also initialize our bit total, so that we'll be able to know how many bits we've sent, and be able to calculate our bit error rate. So as we said that this system is going to consist of two round transmission, where in the first round we have antenna 1 active, antenna 2 inactive, and in the second round we have antenna 2 active and antenna 1 is inactive. So to do that, we are going to define our channels for each round. We start from round 1, where we say that antenna 1 is active, and we define our channel like this by simply generating random numbers, and understanding that the channel is complex. We simply generate random numbers because the channel is random. Practically the channel is random, and we define our H11. As you can see here, we're going to define our H11, we're going to define our H21, and we're going to define our H31. And so we define, for user 1 we define H11, and we define H21 for user 2, and for the eavesdropper we define our HE R1. And then during round 2 now we need to define our channels H12, sorry, and then we also need to define H22 and define H32. And during this second round, where antenna 2 is active and antenna 1 is inactive, we define our H12 and also define our H22 and define our Eve. After now we have our channels, we now generate the signals, or rather the symbols that we'll be transmitting in this particular round, in the first round, because you understand that we have x1 and x2, so we now generate our x1 and x2 to be added in each transmission round, and we simply generate our random bits, and since it's BPSK modulation, we simply do our modulation here by sending it to -1 and 1, and this is x1. We do the same to be able to generate x2 in the same manner. After doing that, now it's time to generate our auxiliary signals. And going back to our equations from our paper, we can say that to generate R2, which is auxiliary signal 2, we simply need to have our channels H11, H21, H22, and H12, as well as X, in order to be able to generate our auxiliary signals according to this design that we designed, that we mathematically modeled. And to generate R1 as well, we simply use the channels. And if we look at here, we already have our channels that we've defined, and we also have our X, or the signals that we are going to send for both user 1 and user 2. So here now we calculate our auxiliary signals R1 and R2, R2 and R1, the same way we did here. This equation here, equation 21 and 22, is implemented in this part of the code. After that, now we come to superposition, which is basically this part where now we add our auxiliary signals plus our user data. So for round 1, we have auxiliary signal 1 plus x1 plus x2. So here now we come and say, during round 1, we have auxiliary signal R1 here plus user plus x1 plus x2. And during round 2, we have auxiliary signal R2 plus x2 plus x1. And here we define the same thing. We say auxiliary signal 2 plus u plus x2 plus x1. Here we call it u1 and u2. After doing this, now we come to we normalize it first. This is how we normalize our signal because now we're going to do round 1 transmission. So now we're processing round 1 transmission. Processing round 1 transmission, we're going to normalize the signal that you're going to transmit, tx1, during round 1, and we normalize it, and then we have this function called guard interval, where we simply add the guard interval to whatever the signal that you are transmitting, and after that we convolve the signal with H11. We convolve the signal with H11, which is basically transmitting the signal, and this is how we convolve it. And then we convolve the signal again with H21, convolve the signal with H21 here, and convolve the signal with HE1, which is the channel of between antenna 1 and the eavesdropper. So after doing that, now we receive our signal at their respective places, Y11, Y21, and Y31. So after reception, we receive now our signal by adding, after convolution here, we add the noises now during transmission. We add the noise to the signal that you're transmitting, and then we receive it here. Now that we've received our signal, because remember that now we've received our signal here. This is the signal received at user 1, and this is a signal received at user 2, signal received at user 2 at eavesdropper. And then we put the signal received there through the to remove the guard interval through this function called remove GI, which is basically remove guard interval. And after removing our guard interval, now we have our Y11, which is the signal received at user 1, and Y21, which is the signal received. This is the signal received at Y11 during the first round, and the signal received at user 1 during the first round, the signal received at user 2 during the first round, and the signal received at Eve during the first round. Okay, now we're done with the first round. We come now to the second round, where we do the same thing. We first of all normalize our transmitted signal so that we'll be able to transmit unity, and then we add guard intervals, and then we convolve with H. We now convolve our signal with our signal here during round 2 with H21. Convolve it with H21. We convolve it with H12. Convolve it with H12. Convolve with H22, and convolve again with H2 Eve. So after that, we add again our noise. This is how we add the noise, and now we have the signal received at user 1 during the second round. The signal received at user 2 during the second round, and the signal received at Eve during the second round. And after reception, we remove our guard intervals again using this function called remove guard interval, and we get the signal received at user 1 during round 2, signal received at user 2 during round 2, and the signal received at Eve during round 2. And so now that we've received our signal, now that we have our signals we've received our signal after round 1 and round 2. Now we sum our signals. Total signal received at user 1 after round 1 and round 2, and the total received at user 2 after round 1 and round 2, as well as the total received signal at Eve. And this is basically how we calculate that. We have the total received signal at user 1 is Y11, which is a signal received during round 1, plus Y12, which is a signal received during round 2. And for user 2, we have Y21, which is the received signal at user 1 at a round 1, and the total plus the received signal at round 2. And for Eve, we do the same thing, which is the received signal during round 1 plus the received signal at round 2. And after doing that, after getting that, now we demodulate our signals, the received signal, using this QAM demodulator in MATLAB, and we get our signals, the signals received in terms of zeros and ones. We do that for the signal received at user 1, the signal received at user 2, and the signal received at Eve. After doing that, now we come here and calculate our bit error rate. And it's how we do that simply is we take for example, for the bit error rate received at user 1, we say that we want to see how many signals that were sent, and remember that x1 for user 1 is interested in getting x1, which is a signal which is a transmitted signal, and for user 2 is the data for user 2 is x2. So for in this part, we simply calculate and see how many signals or how many transmitted signals or data were received by user 1. How many data sent for user 1 were received by user 1. And how we do that, we say the data received by user 1 we see how many of those are not similar to the data that was sent as x1 intended for user 1. And then we calculate now the internal BER by saying we calculate now the BER for user 2 as well by saying by saying the signal received at user 2, how many, we compare that with the signal transmitted, which is x2, the signal that was originally transmitted for user 2. And we calculate our internal BER by saying that, okay, the saved signal at user 1, how many signals, how many of those signals were received by, that was sent for user 2, the signal that was sent for user 2 but received by user 1. We calculate that as internal eavesdropping, where user 1 is dropping on user 2. And for the internal eavesdropping where user 2 is dropping on user 1, we say the signal received at user 2, we compare that with the signal that was transmitted for user 1. And that's how we calculate our internal BER. Now for the external BER, we say the signal that was received by Eve, we compare that with the signal that was sent for user 1. And we get the signal that was transmitted for, and we get the BER of Eve listening to user 1. And similarly, we calculate the external eavesdropping for Eve trying to listen to user 2 by comparing the signal received by Eve with the signal that was sent for user 2. And after calculating our BER here, which is basically getting the in this section here, we are simply getting the signals that the similarity between the received signal and the transmitted signal for each user and Eve as well. We also calculate here the total number of transmitted symbols, or the total number of transmitted bits. And how we come here and calculate our bit error rate by saying that, okay, now we have the total signals that were received divided by now the total received signals that were sent that particular SNR. And we do that for user 1, for user 1, user 2, and we also calculate the internal eavesdropping for Eve. This is external eavesdropping for Eve listening to user 1 and Eve listening to user 2, and we calculate the internal BER as well, where we calculate the BER of user 1 listening to user 2, user 2 and user 2 listening to user 1 in a similar manner. After that, we now come and plot our BERs using this Similogy function, and just to run it and see how it performs. We see that this is our obtained BER, which is our BER plot. And as we can observe, we can see that we have the BER of user 1 and the BER of user 2, which mostly they almost have the same bit error rate. But looking at the BER, let me just zoom inside here so that we can be able to observe clearly. If we zoom inside here and try to observe the bit error rate of user 1 listening to user 2, this is now the internal bit error rate. We see that it is random, which means there is no way that user 1 will be able to listen to user 2. Looking at the bit error rate of user 2 listening to user 1, we can also see that this is also completely randomized. And we can also observe that the bit error rate of if trying to listen to user 1 is also completely randomized, which means that there is no way that if is able to listen to the signal of user 1, and we look at the received signal, I mean the bit error rate of Eve listening to user 2, and we can also see that it's completely randomized. So with this, we come to the end of this part of simulating this proposed model in MATLAB. These codes can be obtained as well in research, so if you want to get a deeper analysis, and you will always get support from us in terms of trying to understand this code and making it work. With that, we come to the end of this lecture, and I hope this lecture has been informative. And if you need to get more details on this technology, you can always find it in research store as an open journal. Thank you.